We step through the examples we have used before to determine an execution time function. Now we will apply the big O notation to specify the time complexity of the corresponding algorithm or program snippet. We call this program that sets the elements of an array to 0 in a while loop. We determine the execution time function to be t of n equal to 3n plus 2. If you don't remember, go back to the previous video to review how we determine the execution time function. We know that we can drop a constant term and a constant multiplier. Therefore, the function t of n is O of n. In other words, this program has linear time complexity. If it is clear that we are talking about the time complexity, then we might also say that this algorithm is linear, or it is O of n for short. The next program snippet performs just one step, no matter what the input size is. The execution time function is O of n. We say that the algorithm has constant time complexity, or short, the algorithm is constant, or O of 1. The next program snippet has a quadratic execution time function, so it is O of n square. In other words, it is quadratic. The fourth example has a linear execution time function. The execution time function is O of n. The algorithm's time complexity is linear. The next algorithm is linear again. This might be confusing as the procedure contains two nested loops, and you might be tempted to claim it is quadratic. However, keep in mind that we measure the time complexity in the input size, so the algorithm is linear in the input size. Finally, we will go through the three elementary sorting algorithms. Selection sort is quadratic, as its execution time function is O of n square. Bubble sort has quadratic time as well. Insertion sort is also quadratic, at least in the worst case, so all three sorting algorithms are the same as far as the time complexity is concerned.